In this video, we're going to learn about translating designs in the UML modeling language into relational schemas. As a reminder, if the application developer is using a high-level design model, then they will create their design usually using a graphical language that's sent to a translator, and the translator will then produce a schema using the data model of the underlying database management system, which frequently is relational. So in our case, we're looking at high-level design in the UML data modeling subset, which is then translated to relations and installed in a relational database system. It's this translation process that's the topic of this video. In the data modeling subset of UML, we have 5 concepts that we learned in the previous video, and we'll see now that designs using these concepts can be translated to relations automatically with one provision, which is that every regular class has a key, and we'll see what we mean by a regular class in a moment. So what we're going to do is go through each one of these concepts one at a time and show how the concepts are translated to relations. For our examples, we'll use primarily the same examples that we used in the previous video where we introduced UML. For classes, we'll have a student class and we'll have a college class. Our students have a student ID, which is the primary key, a student name, and a GPA, and our colleges will have a college name, which we'll assume is unique, so that's the primary key, the state, and the enrollment. The translation from classes to relations is absolutely direct. We take the student class and we make a relation called student. We put the 3 attributes down for that relation, and then the primary key from the student class becomes the key attribute in that relation. And similarly, our college relation has the college name as a key, the state, and the enrollment. So all we're doing to turn classes into relations is basically turning them sideways. So now we're done with classes, and let's move on to associations. We'll see that each association is going to be translated to its own relation that grabs a key from each side of the association. So let's go to our example, the same one we used earlier, that has students applying to colleges. So here's our UML diagram with students applying to colleges, and we'll already have generated the 2 relations for our classes, the student and the college relation, and for the association applied between students and colleges, we create a relation, we call it applied, and that relation has as attributes the keys from both sides. So that would be the student ID from the student class and the college name from the college class. And if you think about it, that makes a lot of sense. Applied is capturing relationships between students and colleges, so we'll capture each one of those relationships with one tuple in the applied relation, identifying the student with the key and the college with the key. Now, one question you might have is, what is the key for a relation that we generate from an association? It turns out that depends on the concept of multiplicity that we learned about in the previous video. So let me set up a generic example of 2 classes with an association, and then we'll talk about multiplicity and keys. Okay, so here we have our 2 classes. We'll call them C1 and C2, and each one has a key attribute. We've called it K1 and K2 over here, and then one other attribute, O1 and O2, and then we have an association A between the 2 classes. So in terms of the relations that would be generated, we'll have for C1, K1, O1 with K1 as a key. For C2, we'll have K2, O2 with K2 as a key. And then for our association A, we'll grab the key from each side, K1 and K2. And the question we have now is, what is the key for relation A? Well, as a default, the key can be both attributes together, but in certain cases we can be more specific. And again, that's going to depend on the multiplicity on our association. Let's suppose that our multiplicity is 0.1 on the left-hand side and a star on the right-hand side. And let's look at what that represents in terms of the type of relationship we're capturing. And I'll make sure to get it right this time. So what this is saying here is that if we have objects of C1 on the left-hand side, each one can be related to many objects of C2 on the right-hand side, but each object of C2 can only be related to at most one object of C1, and some of them might not be related to any. So remember now, it's these edges that are being captured by the tuples in our relation for the association. And we can see that each element on the right-hand side then can be involved in at most one tuple of A. So that tells us that K2 is actually a key for A. So when we have 0 dot dot 1 or 1 dot dot 1 for that matter on the left side or on one side of an association, then the key attribute from the other side is a key for the association. So let's test out that rule on our student and college association and see if it makes sense. So I've drawn the association here, and we're interested in the relation that's going to be generated for the association itself, which will be the applied relation with the student ID on one side, and the college name from the other. So that's the relation that we're going to generate for the association, and our question is, what's a key for that relation? Well, let's add the constraint that every student applies to exactly one college. So that would be a 1 dot dot 1 on the right and then a star on the left, if a college can have any number of applicants. So our rule of thumb, it's actually a rule, said that if we have 1 dot dot 1 or 0 dot 1 dot dot 1 on one side, then the other side would be the key. So that would tell us if we have this 1 dot dot 1 on the right, that student ID would be a key for applied, and indeed that makes complete sense. If each student can only apply to one college, then they will indeed be a key in the applied relation. Now there's actually a related concept here where we might not need a relation for associations at all, and again that depends on multiplicity, and again let's start with a generic example. So here's our generic example, and from this our standard translation would give us 3 relations, one for C1, one for C2, and then one capturing the association A, which would have a key from each side. Now what we're going to discover is that in some cases it's actually possible to fold relation A into either C1 or C2. We'll end up with just 2 relations instead of 3, and we'll be capturing the same information. So let's suppose that we have a 1 dot dot 1 on our left-hand side. So again, we're going to have the situation where from the left side to the right we have a fan out. So each one on the right is related to exactly one on the left. If that's the case, then instead of having a separate relation for the associations, basically for capturing these edges here, we can simply take the related element from the left, the key from the left, and add it to the element for the right. Let me show how that's done. So what we'll do is we'll change this C2 to have K2 and O2 as before, but also to have the key from the left-hand side of class, or relation, so the key from C1, and then we don't need A any longer. And we can see why that works, because every element in C2 is related to exactly one element in C1, so we just add the key for that single element that is related to that relation. Now, what if the left-hand side were 0 dot dot 1 instead of 1 dot dot 1? In that case, it would be possible for there to be some elements in C2 that aren't related to any elements in C1, and that would still be okay with this design as long as null values would be allowed in the third attribute of the relation for C2. And finally, what's the key for this relation? Well, we knew before that the key for C2 was K2, just by definition of it being the primary key for the class, and that's still the case in the expanded C2. K2 will still be a key because we'll only have one instance of each object and the one K1 that it would be related to through the association. So what we saw, to summarize, is that when we have 0 dot dot 1 or 1 dot dot 1 on one side, and then we have an association, instead of making a relation for the association, we can add the key from the side with the 0 dot dot 1 or 1 dot dot 1 to the relation that we generated for the class on the right-hand side. So let's take a look again with students and colleges just to confirm this intuition. So let's again suppose that a student applies to exactly one college, and our rule of thumb says that we have a 1 dot dot 1 on one side. Then we can take the key from that side and add it to the relation for the other side. So we would be adding to the student relation the college name attribute, and we'd be getting rid of applied entirely. And let's just think about it, if that makes sense. If every student is applying to exactly one college, it makes perfectly good sense to just add that college name to the student relation. And furthermore, if we had students just applying to either 0 or 1 college, that would still be an acceptable design, provided that null values are allowed for the college name attribute. Okay, we've finished with classes and with associations. Now let's talk about association classes. Association classes are pretty straightforward. We're not going to generate new relations for them. We're just going to add attributes to relations that we're generating anyway. So let me use our usual example with the students and colleges, and we'll add some information to their application. Okay, so here's our UML diagram. We still have students applying to colleges, and then we've added a association class, which, as you remember, is attached to an association, and it gives extra attributes for that association. So here we're saying when a student applies to a college, we'll have a date of that application and a decision of that application. The first schema that I've shown down here is what we would get if we use the techniques we've already learned without the association class. So the student class generates the student relation, college generates college, and then the applied association generates a relation that has a key from each side. And by the way, right now, let's say that there's no multiplicities or other information that's going to give us special keys. So in that case, the applied relation doesn't have any keys other than the two attributes together. And furthermore, because we have no special multiplicities, we won't be folding that relation into others, as we showed in the previous example. So now what do we do with our association class? Well, as you can probably guess, it's quite simple. All we do is extend our applied relation to include the attributes in the association class. So we just add date and decision right here, and then we're all set. Now there's actually a few things I want to mention at this point. First of all, I discussed in the video on UML modeling the fact that UML assumes when you have a relationship or an association between two classes, there's at most one instance of that association between any two elements of the class. And that is can be seen quite well in this relational schema, because we're assuming we have at most one relationship between any student and any college, and then we have associated with that one relationship the date and decision. A second thing I wanted to talk about at this point in time is the fact that we, for an automatic translation, require that we have a key for every regular class. When I mentioned that at the beginning of the video, I wasn't able to motivate it very well, but this example explains things pretty well. When we want automatic translation, the translation for an association requires a key from each side, and each side is going to be a regular class in that case. So we needed to have a student ID or some key for the student class, and we needed a key for the college class in order to capture the association. On the other hand, here the application info is not a regular class. This is an association class, so we're just defining that as not regular. And we don't need to have a key for this one because we're just adding their attributes to the relation for the association itself. And the last thing that I wanted to mention is that the rules we saw for determining keys for the relations associated with associations and for folding in the relations for associations also work when we have an association class. And it just goes naturally. You just bring the attributes with the association class along with the attributes that you have for the association. You might want to give that a try on an example just to see how it works. But again, it's pretty straightforward. Now let's take a look at how self-associations are translated to relations. It actually follows exactly the same rules, but it's worthwhile looking at to see exactly what happens. So here was our first example of association, which was sibling relationships between students. So in this case, we generate the relation for the class, as usual, student ID, name, and GPA. And then we generate a relation for our association, just following the same rule we already had when we had an association between two different classes. So we need to grab one key from each side. Well, it's the same side that we're grabbing from. So the one thing we need to do is just change the attribute name so that we have two instances of the key attribute from the class, but they have different names. So you can see what we're doing here. We're just saying that we have a sibling relationship. We take the student ID from the two students who are siblings, and that pair becomes a tuple in our sibling relation. And because we have stars on both sides, so we're not making any assumptions about multiplicities, we don't have any 0.1s or 1.1s, then we don't have any key for the sibling relation except the two attributes together. Now, the other example we had in a self-association was colleges being branches of other colleges. So here's our college relation that we generate. with the usual attributes. And then we have our, that's the key there, we have our association, which we're calling branch, which takes a home campus and a satellite campus. And since we've labeled those two sides, we can actually use those labels as the attributes for the relation we generate. So we'll call it branch, and we'll have home and satellite. So that's saying that the satellite, the campus on the college on the right-hand side, is a satellite of the one on the left-hand side. Now these values here will be college names. That will be the domain that we're drawing from, but we're calling them home and satellite to distinguish their roles in the association. Now, what about keys? We said before that every campus, every satellite campus has exactly one home campus, so we write it that way, and that a home campus could have, I think we said something like 0 to 10 satellite campuses. But in terms of generating our relations, the only really important thing is this one-to-one, and if you remember what our rule said, it said that if we have one-to-one on one side, then the other side is a key in the association relation. So what that would tell us is that satellite is a key here, and that does make sense. So we'll only have each satellite's home campus listed once, but home might have many satellites, so the left-hand side would not be a key. Okay, we're getting there. We finished the first three, and now it's time for subclasses. This is a pretty big one. First of all, it turns out that there's, well, at least three, and three commonly used translations from a subclass relationship into relations. So let me set up a generic subclassing setup, and then we'll talk about the three different translations and when we might use which one. So here's our generic setup. I had to draw it a little funny to fit it in the space. S is our superclass, and then we have two subclasses, S1 and S2. And just as a reminder, what this says is that we have objects of type S, and they have a key attribute called K and another attribute called A, and then we have subclasses of those, one called S1, which will have attributes K and A, and will also have an attribute B, and a different subclass, S2, that will have attributes K and A inherited from its parent, and then an additional attribute C. Now there are three different ways, as I said, at least three, that we could translate this UML diagram to relations. In the first way, we have a relation for each of our classes, including the subclasses, and the subclass relations will contain their own attributes plus the key of the superclass. In the second case, we still have one relation for each of our three classes, but in this case, the subclass relation contains all of the attributes from the superclass. And in the third case, we just use one mega relation for the whole thing that contains all of the superclass and subclass attributes. So let's take a look at what the three different translations would produce for this particular setup. For the first one, we'll have our relation for S that's going to have K and A. Then we'll have one relation for each of the two subclasses, S1, that will contain the key for the superclass, so it'll be K, and that will still be a key here for the subclass, and B. So to find all components of an object of S1, we'll get its A component from the superclass following that key, and then we'll get the B component from this relation. And then finally, say S2 will be similar. It will have the key for the superclass and attribute C. Again, what this will require is some assembly to get all attributes of the subclasses. Now let's look at the second translation. We still have the superclass, and our subclasses now are going to contain all of the attributes that are relevant. So they'll have the key attribute from the superclass. They'll also have attribute A and attribute B, and then S2 will similarly have K, and then A, and then C. So in this case, what we can see is that when we have an object that's in a subclass, all of its information will be in its subclass relation, and the superclass will only be used for objects that are in the superclass but not in any of the subclasses. And the third translation says, let's just make a mega relation that contains everything. So it'll have the key attribute K and A and B and C. And in that case, we can see that we may have some null values. So if we have an object that's only in subclass S1, for example, it would then have a null for attribute C. If we had an object that was only in the superclass and not in any of the subclasses, it would have a null for both B and C. Now, as you may have noticed, what has already been on the slide the entire time is that the best translation may depend on the properties of the subclass relationship. And if you remember, we had the properties overlapping versus disjoint and complete versus incomplete. So overlapping meant that we might have objects that were in more than one subclass. Disjoint meant that's not possible. Complete said that every object that's in the superclass is also in at least one of the subclasses, where incomplete meant that said that there would be some objects, or they could be, that are in the superclass and not in any subclasses. Sort of alluded to how some of those properties affect the different translations, but let's look at it very specifically. Let's suppose, for example, that we had a heavily overlapping subclass relationship. In other words, we have many objects that are in multiple subclasses. If that's the case, then we might prefer design 3, because design 3 captures all of the different attributes in one place. So if many objects have all those attributes, we might like to just have them together rather than needing to assemble them from the different pieces. On the other hand, let's say that we have a disjoint, and furthermore, let's say it's complete. So we have every element being in exactly one subclass, and there are no elements that are in just the superclass. So in that case, we might like to use design 2, because design 2 puts each object in its individual subclass relation, and furthermore, since it's complete, we could actually, in this particular case, get rid of the first relation. We wouldn't need that, and so the best design would be number 2, modified to only have the subclass relations. So now let's revisit our gigantic example from the UML modeling video and see how that would be translated to relations. So just to remind you what's going on in this big diagram, we have students, and students have a student ID and a name, and then some of our students might be foreign students and they have a country. Some of our students may be domestic students and that they would have a state and a social security number, and we'll assume that every student is either foreign or domestic. And then some of our students are AP students, and interestingly they have no attributes, but those are the ones who have an association called TOOK with AP courses. AP courses have a course number and a title, and then when a student takes an AP course, there's an association class that says the year they took it and the grade they got. So let's translate this to relations, the whole diagram. And we're going to use the first translation from our 3 schemes. So that's the one where the subclass relations contain the superclass keys and then all the specialized attributes. So let's start by generating the relation for the student class, and that's straightforward. That's just the student ID and the student name, with the student ID being the key. And then we're going to generate one relation for each of our 3 subclasses. So that would be the foreign students, which will take the key then from the student relation, so their student ID and the country that they're from. There'll be the domestic students, and there we'll have again the student ID inherited from the superclass, and the state they're from, and their social security number. And then we'll also have the AP students, and those have none of their own attributes, but we can get the key, and we do, from the superclass. So this is just going to be a list of the student IDs who are AP students. Now let's keep going. So let's take a look at AP students taking courses. So we'll have from the AP course class a straightforward translation to the course number and the title of the course. And then finally we're going to have a relation for the fact that an AP student took classes. We had some multiplicities on that the first time, but neither of them were 0, 1 or 1, 1, so they're not going to be relevant in changing our design. So took is going to have the key from both sides. Well, we don't see any key in here, do we? But subclasses always inherit the key from their parents. So the key here is implicitly the student ID, and that's what we'll be using here, student ID, the key from the right-hand side, the course number that they've taken, and then we'll have the 2 attributes from the association class, the year and the grade. So this actually looks like a pretty good design. Let me just make a few comments. The first one has to do with the AP student relation. So if every AP student does take at least one course, so if we have, for example, a 1 ... something over there, then we could actually eliminate this relation, because every student ID that appears in AP student will also appear in the TOOK relation, so this one will be redundant in that case. So again, that could be eliminated based on the multiplicity, though I wouldn't really expect an automatic translator to necessarily figure that one out. Another possibility I should mention is that we could have a primary key specified here for domestic students for Social Security numbers, since we would expect that to be unique, and that would translate to a key here. But let me be clear, this would be a separate key. It wouldn't be Social Security number and student ID together, but these would be two different keys. And in SQL you can actually distinguish between those two, but we can't do it the way we've written the relations here. And finally, let me mention again that requirement that we have keys for regular classes if we want to do translation automatically. And you might have noticed that, for example, we certainly didn't have a key here for foreign student, with country being the only attribute. But subclasses are also not considered regular classes. So subclasses and association classes don't need to have keys, and we can still have an automatic translation. Logically, subclasses are inheriting their keys from their superclass, and that one does need to have a key in order to have automatic translation. Whew, so that was a big one, but you'll be glad to know that composition and aggregation is going to be quite quick. So here is our example where we have our college class as usual, but colleges contain departments, and this solid diamond here is the composition operator that says that we have objects from the right-hand side class that are components of the left-hand side objects. So let's look at the translation to relations. We'll translate the college side as usual with the key attribute, college name, and the other attributes. And then, although this is an association, we're not going to have a separate class for it. We're going to have the right-hand side class have both the values of the objects in that class and the association captured together. So we'll have a relation called department, and it will have the department name and the building, and then it will also include the key of the object it belongs to. So in this case, that would be a college name. Now, if you think carefully about it, this translation actually makes a lot of sense and is consistent with what we've already done. We said when we introduced the notion of composition that we effectively have, by definition, a 1 ... 1 on the left-hand side of the composition. So if we treated this as a regular association, used our regular translation, and then used our rule that allowed us to get rid of association relations, we'd actually end up at exactly the same design. By the way, this is the last example where we have a class that's not one of those regular classes that require a key. We don't have to have a key for the right-hand side of a composition in order to have an automatic translation. Aggregation, by the way, was the case where we have the empty diamond, and that's implicitly a 0 ... 1 instead of 1 ... 1. We had an example with apartment buildings. I'm not going to bother to give that one again. But in that case where we have aggregation rather than association, all we need is the same design, but the ability for that key we're grabbing from the left-hand side to be null, and then everything works out fine. So to conclude, the data modeling portion of UML is a popular high-level language for database designs. It's graphical, and it can be translated automatically to relations as long as every regular class has a key, and that typically is the case.